So, welcome back everyone. We are studying NPTEL course on topological phases of matter, and we have taken example of Schrieffer-Heeger model for one dimensional topological insulators, and now we are discussing two dimensional case. Okay. Two dimension means kx and ky, two spatial dimension, and we have taken Hamiltonian, which has all the, so 2 by 2 Hamiltonian are still we are studying, and we will go to 4 by 4 later. So, in the 2 by 2 Hamiltonian, it can be written in terms of Pauli matrices, and we already discussed that the diagonal terms, which are the trace of the Hamiltonian, do not contribute to any of this topology. So, we have ignored it, we have set it to be 0. So, then we have D3, which are the diagonal term, but it is the difference between the two bases, the energy difference between the two bases. And then you have D1 and D2, which are the inter basis hopping terms. All right. So, then we have all the three terms, and if you have all the three terms, the Berry connection turns out to be again it kind of a cross product between dA with a derivative along mu directions multiplied with dA with an antisymmetric product between them, and it is the denominator is what I want your attention. So, you can see that the denominator has two terms. One is this term. So, when d goes to 0, that means when d1, d2, d3 all three go to 0, this diverges, and when d becomes equal to d3, in that case d may or may not be 0. So, if it is not 0, then this is another important point, which turns out to be the north pole and south pole. Okay. And this sort of denominator, however, disappears in the difference between them, between the connection, and we want to see where such things appear, and then the Chern number will depend on this. So, then we are going to talk about two special cases. In the first case where d equal to 0. So, that means the two band has to touch at k star. If they touch at a given point, we will have Dirac cones, Weil cone in 2D and 3D and even in 1D. In 1D we have already seen it, and if it does in a contour, we will have line, nodal lobes and so on, and we will talk about these things in details. The second one is when d3 d equal to or d equal to plus minus d3. In that case, d do not go to 0 is the one that we are interested in, and obviously then you will have a gap, and that gap will be created by this guy, right, because energy is equal to plus minus d, right. So, it will be the gap, it will be created by this. But then again we will have two situations where d3 has a fixed sign or d3 changes sign. So, if d3 changes sign, we will have a Chern insulator. Okay, so, let us just put that into some figure. So, in the case of, let us start with the third case where d3 changes sign. Okay. So, let us say this is my kx, ky, and this is the called gamma point, which is 0 0, and let us assume that there is this contour in which where D3 goes to 0. The gap goes to 0, which means the gap must be changing sign. So, this is a region which is, let us say, D3 is less than 0, and this is the region where D3 is greater than 0. It can be the other way also. In that case, the Chern number will change sign. Okay. And we have already seen from this expression, as D3 changes sign, you go from one Berry connections to another. In this case, D3 do not contribute here. So, which also means that that's automatically gives us the opportunity to have the connections to change sign. So, let me remove this. A minus, and this will be, let me use a different color. Alright, and this is a region where it sort of not well defined, which is okay, because in the difference it does not matter. And these are the quantity for the same band, although I am using plus minus because that is the expression we used, but the point here is that, and that we have seen that in one dimension, that the point is that it will be in the same band. It is just that in the same band you will have eigenvector changing from plus to minus eigenvector. Okay. So, then in the band structure, and I am plotting along some high symmetry direction, which can be any direction you choose, going from diagonal or this way. Okay. And this point where the K star is, and minus pi, or yeah, this is gamma. So, I am sort of going in this direction, let us say, and this is plus pi, in fact minus pi, in this case plus pi, and if you do this way also, you can see that it does not really matter. Okay. So, inside you will have this band, and outside it will change to this, and here it will be other way. Okay. And that is clear from the eigenvector. You can actually also go back to the eigenvector. You can see that, I am not sure if it is written here. Yes. So, you can see that the eigenvector also changes from, so as the D3 changes sign, as the D3 changes sign, you actually go from this eigenvector to that eigenvector within the same band. And that is what we denote. Okay. So, in this region then you will have, let us say, A minus, and in this case then you will have A plus within the same band. Right. And if it is a trivial case, then so this is the non-trivial, and obviously the trivial case would be in this case this contour will gradually goes to 0 either this point or with this point. So, that means it is going out of the Brillouin zone, or it is sort of going away sort of vanishing at the gamma point. So, in these two cases, when the D3 will come here, so D3 will become 0 here. So, this contour, when it will vanish here, you will have a Dirac cone here. Why? Because I have obviously I am choosing D1 and D2 to also vanish here, that I have we have assumed it, that is the form. So, you will have a Dirac cone here. In the cases where this becomes larger and vanish here, you will have Dirac cones here. Okay. In both cases, you are going from a non-trivial case to a trivial case, in which the entire Brillouin zone will be covered by just one band with one eigenvector and with one plus or minus, not a change. So, the lesson is, of course, D3 also has to change sign, but D3 does not have to vanish at the same point and every other points are vanishing, but D3 must change sign. So, that means it is also going to 0 at some point, which the band structure is not saying it, because and at that point D1 and D2 are not 0, but the eigenvector is wrapping around it, because when D3 goes to 0, you have a singularity, you have a hole. Yeah, actually I can draw that here. I probably should have done. So, in the non-trivial case, you do have the d equal to 0 point here. Your eigenvector can be at some point theta and phi, right, and the other one will be at the antipodal point. And these 2 points corresponds to the singularity, north pole and south pole, where d equal to d3, d equal to minus d3, and this is the point where d equal to 0. This is the case for non-trivial. For trivial case, you will have it somewhere here, because D3 is not changing sign. So, in fact, D1, D2 changes sign. So, you should go through this. If the D3 has the fixed sign but negative, it will be somewhere here, and at the point the Dirac cone happens, it will touch here. Okay. And let us see that again with an example, and this is the famous example. It is still a toy model. We will talk about real material, the tight binding model called Rice Mele model. So, D1 is taken to be sin kx. We can have some, generally you will have some hopping, but okay, let me finish it and then I will talk about. And some square lattice. Okay. Okay, it is just a square lattice. And so that means in the lattice will be and now we see that this is still a 2 by 2 Hamiltonian. So, at every side there must be two sublattice and we will call them A and B. Okay. And let me remind you, so if you write this in terms of the Hamiltonian, so it will be m plus cosine kx plus cosine ky, and it will be minus sin kx minus I complex conjugate. So, what each term corresponds to? So, this one corresponds to the same site, same orbital, same sublattice hopping between different sites. So, m corresponds to the on-site energy difference between the A and B site, and this term comes from the hopping from this side to this side and the other side and y direction. And you can have a overall tight binding hopping T, right. T which can be same or different, but we set it to be 1 because it will make the calculations easy, but it won't make any difference in the overall property. Okay. So, we will set it to be 1. And the same thing for this. So, where does this term come from? This one is the hopping from A to B, A to B and so on. This is the real part and this is the imaginary part, and these are sign means the hopping from this side to this side has amplitude, let us say t prime, from this side to this side the hopping is minus t prime. Then you will get a sine term and then you will get a sine term along y directions if you have the same thing. So, that means you do need some special lattice to get such term, and we will find that these are very important term to get it. And with graphene, with spin orbit coupling, Raspa spin orbit coupling, and also if these two orbitals have different parity like a s orbital and p orbital, such things also can appear. Okay. And these things are just the same hopping T along all directions. So, why did we choose such term? Simply because now we see that d1 goes to 0 and d1 goes to 0 equal to d2 at k equal to 0 0, which is called the gamma point, and plus minus zero, we will call it x point, or 0 plus minus pi, which we will call y point. And the equivalent points. Okay. And so, our conditions are already satisfied that d1 d2 goes to 0 irrespective of any parameter. So, it is the d3 then. Okay. So, this takes values from minus 1 to plus 1, it takes value minus 1 along again all these points, minus 1 or plus 1 along all the high symmetry points, but the maximum and minimum value it takes. So, obviously, the maximum value it takes will be equal to m plus 2 at gamma point, and will be m minus 2 at plus minus pi plus minus pi, which we denote by m point. These are the m points, and these are the equivalent points. Okay. So, these are our main points, which are also called time reversal symmetric point, that we will study later. Why do they are called? But these are the main points that we need to look at. So, the topology of the theory will depends on how all the actions are going to happen at these points. So, now you can see that if D3 has to change sign, M must be less than equal to minus 2, greater than equal to plus 2. Within this region you can have a topology. Okay. Okay, let us define something called m prime equal to m plus minus 2. So, actually we will define it later. So, these are the values of m. So, m is our only parameter in the Hamiltonian. Okay. And let us put minus 2 here, 0 plus 2 . Okay. All right. Yeah, in fact, okay. So, we will take one case at a time, and with all our discussions I can go first saying that if I draw a band structure, so this should be a trivial band. Because m is less than minus 2, so D3 does not change sign. So, in the Brillouin zone you will have A minus for the lower band, and in this space D1, D2, D3, the eigenstates live on a D vector that will be somewhere here. Yeah, it will. So, D3 does not change sign, right. So, what happens at m equal to minus 2? So, at m equal to minus 2, this guy goes to 0 at the gamma point. So, D3 goes to 0 at gamma point, and D1 and D2 also go to 0 at gamma point. So, we will have a Dirac cone at the gamma point. At gamma. So, at this point so here the topology is not well defined, because A sort of diverges at this point. Okay. and at some value the surface of the eigenvector just touches the singular point d equal to 0. So this is the region where m is minus 2 less than but less than 0, greater than minus 2 and less than 0. So you can take m equal to minus 1 as an example. So here d3 equal to 0 contour will be obtained from here by solving this, setting this to be equal to 0, you can figure out, and it will depend on the value of m. And you can see that near the gamma point okay, we'll do that. You can expand it near the gamma point in terms of k, then you can obtain it, and here it will be some band inversion has happened, right. And in this case you are wrapping about it in 2 dimensions. So again this will be a minus, this will be a plus. All right. So again when m equal to 0, what happens? When m equal to 0, when this is plus 1, this is minus 1, you get, they vanish. So they vanish at this point, and in a contour. So and obviously d1, d2 also go to 0 here. So that means you will again have a Dirac cone, and the Dirac cone will be somewhere here. Okay. This is x point and this is minus x. Okay, and again you can draw that it will be somewhere here. Actually it doesn't matter where it is. Okay, now comes to this region, and it will be opposite to this one. So m is greater than 0 but less than 2. So again you will have a band inversion. Okay, at some point k star. So now this k star will, you actually write a small Python code to do that. It's very easy to see. This is y point, x point, m point, gamma point. Now the band inversion is going to happen along this contour, d3 equal to 0. Okay, and here again it will be some And now m equal to 2, you will again have a degeneracy now the degeneracy will be at m point, but this guy is going to shrink to this point, right. And finally, you will have a trivial insulator. For m greater than 2. So, everywhere it will be the same. All right. So, this is the picture. So, you will have a topological then insulator from this region, and it should change with the Chern number being +1 to -1 in this region, topological insulator. Also topological insulator. These are trivial, and these are the Dirac points. So, now the calculations. So, we already identify that all the actions are happening either this point or this point or this point, right? All these isometry points. So, this is where we can identify if they are going to 0, and one more point where the band inversion is happening. So, band inversion might be happening around the gamma point in this region. So, you can expand the D3 term near gamma point or near M point, and here as you can see that the Chern number remains to be 1 all the time. So, that means whether the contour is smaller or larger, it does not matter as long as it does not touch this boundary. So, this entire region from here to here, the D3 contour goes to 0, they are all homotopic, these loops. Okay. So, with that what we can do is that we can expand, and these are something that again we will come back how these expansions are done. Called K dot P model with some Taylor expansion. So, what we can do is that we at gamma point D1 is like near gamma point, D1 is like the leading term of sin kx is kx, leading term of sin ky is ky, and D3 will be m plus 2 minus, so it is cosine kx square minus 2 cosine ky square by 2 cosine ky. Okay. At m point D1 is, so we are now expanding near pi. So pi plus kx will give us minus kx minus ky, d3 will be m minus 2 and let's take one more point d1. So this is near pi 0, so it will be kx, dy will be ky, d3 will be m plus 2 plus ky by 2 and y point it will be opposite. Actually I made a mistake, it goes to 0. Okay. So even if we ignore this term, exactly near these points, even the quadratic term can be ignored and we just take the leading term, then you will have only these terms. So you can see that one thing that you can see that whatever happens at x point and y point, they always complement each other, dx and dy and these 2 points. So any Berry curvature, anything that happens in this point just will completely cancel each other. So we just have to look into what is happening between these 2 points. Okay. So let's look at the curvatures for minus band near gamma point or near gamma or m point. So it will be minus ky divided by 2d d plus minus plus m plus minus 2. So let's define this quantity as m prime, and then ay will be again around m and m point, kx divided by 2d d plus m prime, where d is equal to, now dA1 square is kx square, d2 square is ky square, so it becomes kx square plus m prime square root. Okay. And f xy for minus band is equal to m prime divided by 2 dq. Chern number. Near gamma point. So it turns out is that these guys are singular this is singular around these points only, and what these are also singular here, but we just talked about that these two will completely cancel each other. So only we need to look into these 2 points. So we are just looking into gamma point, and then it will be the or the total Chern number is and we can just near gamma point plus near M point. Everywhere else they are sort of trivial or they do not contribute much, they will just cancel each other. Only these 2 points you will see from all this expression that they contribute. All right. And let us call it C gamma plus C M. So C gamma then can be written as M prime divided by 2 pi times 2 divided by, so this one, right, M prime by 2 I have taken it out, so it is D cube, and D is this one, so M prime square plus K square 3 by 2, okay. And this integration is now becomes K dk d phi in the Brillouin zone, and so we are somewhere at a gamma point. So what should be our contour? So contour can be a small contour anywhere up to where d3 goes to 0. Any small contour, big contour does not matter, because this one is only singular around the k equal to 0, around this point. So any small contour and all you choose does not matter, it is like a solenoid. So the electron is moving in a larger or smaller, it does not really matter, its contour. So this integral now can be done, and what you will get is so it just depends on the sign of M prime, which is the mass. So D3 is M prime, right, which is equal to M plus minus 2 at gamma point and M point. So and Cm, if you do the same calculations, you will get, so the total Chern number is C gamma plus Cm is equal to sine of M plus 2 by 2 plus sine of M minus 2. So now you can see here sine of M is fixed, so they will, actually I made a mistake, it is minus or sine of M, so yeah, it already takes care of it. Alright, where is it? Okay. So then this is equal to 0 if M equal to 0, this is equal to then plus 1 if M this region and equal to minus 1 if M is greater than 2, greater than less than 2. That is exactly what I did here. This is my chart number 1, this is chart number 0, this is chart number -1. So, let me draw this again. +1 -1. Topological insulator or called Chern insulator. This is also Chern insulator. These are trivial insulator and trivial. These are the Dirac cone or semi metal, and also this region, this point, this point. So, as M changes, which you can change through strain or M is the onset energy. As M changes, you have a trivial insulator, band insulator, then you get a band degeneracy with a Dirac cone, then a topological insulator phase transition happens. Then one topological insulator changes to another topological insulator. Both has different topological invariant, +1 and -1 Chern number. And then again, and that transition also happens through a semi metal Dirac cone. So, band again has to invert, but again it inverts from a one inverted case to another inverted case. Then it becomes again trivial with the band inversion happening here. So, every band inversion requires a band gap closing at a single Dirac point. Okay. So, this is the model description of topological insulator Chern number in 2 dimension, and we will take another example called Holden model, which is on a graphene. And in that process, in the next class we will start with looking into Dirac cone, Dirac semi metal, and before we take an example of Holden model. All right, thank you very much for your attention.